taking Xerox for the class. Yeah. Give it back to me on tomorrow. So we are doing derivative calculations in last class, right? So set of derivatives we have done, and then we also have seen Cp minus Cv equals to R for the ideal gas. Cp by Cv equals to kappa T by kappa S, right? Kappa T by kappa S, which is the gamma, which is so kappa T is the isothermal compressibility, kappa S is the height.
That's in one derivation that A equal to U minus Ts. So when you're differentiating it with respect to P or T, so there's a term S coming in the right hand side.
Yeah, that's okay.
Okay,
S coming right hand side. Yes, I know that. In that case, you have to keep in terms of S, and in that case, entropy has to be defined. Without entropy definition, without entropy property, you cannot get the derivatives. Yes, yeah. There are a lot of cases we will see that. So entropy has to be known. Is a Helmholtz free energy? Yes. Yeah. It will happen. Or even Gibbs free energy also. So we also have proved last class Cp minus Cv equals to R, Cp by Cv equals to gamma, and also we have proved dou Cp by dou P at fixed temperature, which is minus T dou 2V by dou T square. Right, you have proved it, right, last class. Now, next proof I will give is dou Cp by dou V at fixed T. Dou Cp by dou V at fixed T. How to prove it? You know that how to prove it. What's the first step? What's the first step to prove it? How should I start with? Because we know that Cp and Cv, the formula is Cp by T, dou S by dou P at fixed T, Cv by T, dou S by dou V at fixed T. This formula always you have to take. That's the first catch. So we can see that Cp by T, this is the formula we have to use because Cp is given. So this is the first step. We should not take this is the only formula you have to take because that's the way you can get all your things done. And then how will you proceed? An advantage of this thing is these are the why I am taking this formula because these are actually coming in the Maxwell's relationship, right? This formula, and this will give directly the property estimation. So with that actually you can directly correlate your variation with the material properties. So that's the one of the major advantages. So what's the next step for dou Cp, dou Vt? Cp by T. So first step is dou V Cp by T. Okay, at constant T. What will you get? Next step. Next step, what will you get? Yes. Dou V not into T won't be there, it was Cp by T. Dou S by dou P at constant T. Okay. Next step. We can write this as yes. Next step. Dou S by sorry. Sorry for my mistake. Okay, apologize. Sorry for that. So this is how to proceed further. Dou S by dou T at fixed P. This is a constant temperature. for information. Next step. Maxwell will be there? No. Maxwell will not be there because not such a number. We can exchange because thermodynamic property. Is that correct? Yes or no? Yes? This is we know, right? What is that? Any hands please? Yeah.
Dou P by dou T.
Minus dou V by dou T? Yes. Minus is that correct? Now T should be going out because T is constant, so you don't take differentiation. So it will be dou Cp or with respect to dou V at constant T, it will be minus T dou 2E by dou T square P with dou V at constant temperature. Is that correct? Yes. Any confusion? Correct, no? Next is dou Cv. Now I give you the problem. Dou Cv by dou V at constant temperature. Let's see who can do it. Dou Cv by dou V at constant temperature. Dou Cv by dou T, dou Cv by dou V at constant. What it should be? Any hand please? Yes. At constant? Yes sir. See, you know now you know very well. So T, dou 2T, dou T2, V. Right? So you are very comfortable with this, right? And similarly you can also find out dou Cv by dou V at constant temperature. So you can see Cv and Cv, they depending on pressure and volume, and it is easy to find out in terms of material properties. So for particular materials, whether it is solid, liquid or gas, you can easily find out the variation of Cp, Cv with respect to pressure and volume. Okay, at constant temperature. Okay, generally speaking, Cp is given in the function of temperature already. So in that case, dou Cp by dou T, you can actually take it out. You can see that in chemical reaction engineering, if you look at heat of reactions about, and there you can see Cp, Cv. In fact, while you see house loop, you can see the Cp and Cv, that the function of temperature and polynomial is given. So another things we calculate, so it's called Joule-Thomson coefficient. You might have heard in physical chemistry, Joule-Thomson coefficient. Joule-Thomson coefficient. And there is a Joule inversion curve. So please read from internet or physical chemistry book. I am not going to discuss this. At least you can read more, you can actually get more information. So go to Google, search for Joule-Thomson coefficient, it will give you the curve. What actually I wanted to know that Joule-Thomson coefficient is defined as mu equals to dou T by dou V at constant H. How to calculate? That's what I am interested in. Mu equals to dou T by dou P at constant H. How to calculate that? Or you can put small h, no problem. This is Joule-Thomson coefficient. We sometimes write mu Jt. Joule-Thomson coefficient. How to get mu in terms of material properties? Any idea? Who can give the catch? Dou T by dou P at constant H. Joule-Thomson coefficient. How to evaluate? Yeah, any hand please? Yeah, you may be wrong, no problem. Yes. One step. Just one step. You know the rules. Everything has been taught. You know the rules. What is that? Who is saying? Yes. Can you tell me? Tell me now, please.
Equal to minus dou H by dou P.
Dou H by
Dou P
at constant T, dou H by
dou P at constant
P over. That's the catch. And then dou H by dou P at constant T. What is that? You have done it. So go back to your plus notes. Supply me the formula. This is Cp. No problem. Minus B into, minus is there, B into 1 minus T beta. Done. So that's the way Joule transfer coefficient is evaluated. Okay. Now I will discuss some derivatives which are there in your assignment number 1, assignment number 2, first problem. If you look at, I have given so many derivatives, right? Yeah, so many derivatives are there, and they are basically based on 3 processes: isoenthalpic process, isoentropic process, and free expansion. 3 processes actually I have given. So first one is I have given as isoenthalpic process. Number 2 is isoentropic process. Number 3 is free expansion. Here H is constant, right? Here S is constant, and here last step U is constant. Free expansion. So now I won't do the whole set of derivatives. I will do some 1 or 2. Then you can practice at home. I want to derive the formula for dou S, dou V at H. Earlier you are deriving like dou S, dou V at fixed T or dou S, dou V at fixed P. Okay, that means what we were doing earlier, temperature was constant, isothermal process, isobaric process. Earlier I was doing, or isochoric process. Now I am doing isoenthalpic process. So we have, what earlier we have done? Isobaric, isochoric, isothermal. Now I am doing isoenthalpic process. So this says that we have to write S as a function of V and H. That is a very difficult task. How to proceed? How to proceed? See, U, V, and then from there how to get H? But that is not the way. We have some usual procedure, right? I won't write H equals U plus V, then everything is gone. I will do our way, what we have learned so far. Please go, otherwise if you do arbitrarily, you will be lost completely. I don't want to be that. How to proceed? S is the final approach. We know S is the function of U and V. We know S is the function of B and T. We know S is the function of P and Q. All those things are known. With that, can you start with? Any idea? With that, can you start with? Yeah.
So S is a function of H and P.
S, H and P.
So matching function.
Okay, then?
So then we figure about S is a function of.
Then P. Then P is the function of B and T. Then we are expressing S as a function of HPT. Three terms. Dangerous. Any luck?
S is a function of P and T.
P and T, yes.
Then we go for infinity.
Implicit function means?
Like we can express in terms of dT by dV and dT by dou T by dou V and dou T by dou V. So from there we can
No, that is not the way I do know. I have a procedure. Otherwise, if you don't follow the procedure, you are lost. Don't take any other procedure. You know what we have done earlier. Even when you did dou u by dou v at fixed t, we know that u equals to u hat sv, and by the time s is already known, we did u s as function of v and t, v, and then we got u bar v and t. That's the way we actually did earlier. This kind of, I want to follow the same procedure. If I go by any other procedure, then I am lost. I want to follow the same procedure. No need to just think that, tinker around here and there, then you are really lost. Don't try to do anything. You just see from the first principle. It's just like a first principle. How to do that? I want to do it from the first principle.
This is a function of v and u.
S as a function of v and u, then
U as a function of h and v.
u is the function of h and v.
And directly
H is the function of u and v. Are you correct? No. H is the function of s and p. Don't try to do something wrong here.
h as a function of u and v.
U and v, correct?
U as a function of h and v.
What? U as a function of
H and v.
h is a function of. Okay, let me write down. Du equals to tds minus p dv. dh equals to tds plus v dv. dA equals to minus s dt minus p dv. dg equals to minus s dt plus v dv. Am I correct? Yes. Only you have to know, remember this, and you can. So now you can see that s is the function of h and p, and p is the function of b and t. So you are getting h, p, t, three terms. Dangerous. I will go by this formula. I know the approach. Don't change the approach. If you change the approach, you are gone. You should not change the approach. You should not change the approach. So no luck. I wanted the answer from you. I would have been very happy, because then only you can think and then give some answer and get satisfaction. We know h is the function of b and t. Right? So from there, we know that if z equals to z hat xy, we can write y equals to y hat xz by implicit function theorem, provided I am not working with 4 degree centigrade water. So that we can write as t is the t hat vh. Yes or no? I have done in the class. That means this h we can actually we can see that that t we can write in terms of v and h, and then when we start doing the work, 2s by dou v at fixed stage, where what is your function s hat vt, and then we can write this as v t hat vhv, and then you are going s bar vh. Am I correct? Yes or no? Yes. So I have to take my working function as s hat vt. Am I correct? So if I take s hat vt, we can get s hat vh, provided this is valid, and I am assuming that I am not working with the 4 degree centigrade water. If I am taking 4 degree centigrade water, that will not be relevant. Okay, that's the main assumption. And of course, most of my substances, I don't expect any phase change or any kind of phase change. So here we can write ds equals to my working function dou s. Who will give me the step? Dou s. Any hands? Yes. Dou s by dou v at t dv plus dou s by dou t v dt. Next step, I have to find out dou s by dou vh. Next step. Next step.
Dou s by dou v.
Dou s by dou v at fixed t. You should get all s fixed t.
Dou v by dou v.
Dou v by dou v fixed h. Dou s by dou t fixed v. Dou t by dou v at fixed h. Dou v by dou v is 1. S by dou Vt is coming from Maxwell's rule, isothermal. There are 4 rules, Maxwell's rules. Third rule, you can just see it, check it out. What is that? Dou P by dou T at fixed V. Then dou S by dou T V is Cv by T. Am I correct? Dou T by dou V at fixed stage. How to get it? That's the now catch. How to get? We have not evaluated earlier. We have lost here, right? How to evaluate this? Dou T by dou V at fixed stage. Dou T by dou V at fixed stage. Any hands, please? Implicit function theorem again, madam. Please, you know the answer. Minus dou H dou V at fixed T divided by dou H dou T at fixed V. Dou H by dou Vt we know, we have done it, and dou H by dou Tv we know. So that's the way we can get first derivative of the isoenthalpic process. Not clear? So I have not used any other formula. I just use the same formula what we have done to the first principle. Right? Next is dou U by dou G by dou T at fixed stage. 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 G equals to H minus Ts. So dou G by dou T at fixed stage, H, dou H by dou T at fixed stage minus T, dou S by dou T at fixed stage minus S, dou T by dou T at fixed stage. This is 0, H constant. Okay, and then minus T, dou S, dou T, dou H will be there, and here minus 1, right? So we have dou S by dou T at fixed stage will be obtained from isoenthalpic process. How to get? S is the function of Vt, and we know that S hat V T hat HV, and we get S bar. No, this won't work. How to get it? HT. S is the function of HT. So this T is fixed. We cannot change it. If we change, we have a big problem. How to get my final function? H, T comma H, right? This has to be a function of T comma H. How to proceed? So question is, can you express V as function of H and T? Yes, H is the function of V and T. By implicit function theorem, you can write. So that's the catch. That's the catch. So I know that H is the function of T and V, and from implicit function theorem, we know that we had HT. So S hat, V hat, HT, T, and that's it. Whole lot of, I think, derivatives you can do it now. I have given the technique. Technique is, the master key is with you. You know how to apply the different rules and formulas. Next I will go to, I think isoenthalpic process is over. Now we will go to isoentropic process. We will go to isoentropic process. We will go to isoentropic process. Isoentropic process, dou U by dou V at constant S. We know that temperature, the first law of thermodynamics is very straightforward. If I want to find out dou H by dou V at fixed S, dou H by dou V at fixed S, that means you have to express H is the function of S and V. It says that H is the function of S and V. We know that, so always you use this kind of formula, it's better. Vt Tp, whatever property, you take dt and dp, and then you know these kind of things, and then we know S equals to A sat Vt, right? Yes. So V we can write this as S and T, or T you can write as S and V, whatever. So you can, from here you can write T equals to T hat SB, correct? You write T hat SB, so you got finally V is V, H is SB. That's the catch. Very simple. So what we have learned for this kind of isothermic, all the processes either have to express in terms of V and T or P and T. V and T or P or P and T, and then with that we can have the German. So any property you take, H is the function of V and T or P and T, S is the function of V and T or P and T, U is the function of V and T and P and T, and then apply the implicit function theorem, and that's it. You got the result. So we have dou H by, so H is the function of V and T. This is my master equation, right? Which is nothing but H at V T S V. Am I correct? Yes. dH dou H dou V at constant T dV plus dou H dou dV dt. Then you have dou H by dou V at constant S, dou H dou Vt dou V dou Vs plus dou H dou dV plus into dou T dou V S. This is 1, and dou H dou Vt is already known, right? Dou H dou TV is already known, which is Cv. Not CV, something is there. I'm not sure what's the value. And dou T dou Vs, again you use implicit function theorem, which is minus dou S dou Vt by dou S dou TV. And that's it. Now you are a real expert how to evaluate all these derivatives. They are not that difficult, they are very easy, because the basic principle is, we have to express any of this thermodynamic property either the function of temperature, pressure and temperature volume. Please note down that you have to do this kind of principle so that you can evaluate. Similarly, one can actually do the free expansion. The same thing will apply, for example, if you want to calculate dou S by dou P at fixed U. Dou S by dou P at fixed U. If you want to calculate dou S by dou P, at fixed U, always we start, since P is there, your final function is PU. So how to start with? Who will tell me the first step? How to start with? S equals to S hat? TP. Pardon? TP. TP or PT. And then next step, you have to get your final function PU. Then next step is so straightforward. P is there, you have to express T as the function of P and U. Yes. And it's possible because you know that U is the function of P and T. So T is the function of U and P. So we can write this as S hat P, T hat P, U, and this, and we have ds equals to dou S dou Pt dP plus dou S dou Tp dt. Then we have dou S dou P at fixed U, which is dou S dou Pt dou P dou Pu plus dou S dou Tp dou T dou Pu. Right? So dou S dou Pt, that we know, right? Dou P dou Ph is 1, so equals to 1 because dou P by dou P, dou S dou Pt we know, and dou T dou Pu by implicit function theorem, right? Which is nothing but minus dou P dou U dou Pt by dou U dou T Pt. So you can evaluate all derivatives. Same principle I am actually using. not a different thing. I'm expressing my thermodynamic property is a function of either temperature, pressure, or temperature, volume. That's it. The job is done. Okay. So I think that's enough for this thermodynamic property and derivatives. Next will be, now we are seeing that we are mostly concerned about the derivative like dou P, dou B T, dou P, dou B T, or beta or gamma, all those things. So most of the time we are concerned with this type of derivatives. If we know for different materials, then your job is done. That means for materials, or we have to write somehow like this. So this information is very important. If we know this expression, this functional form, we can calculate, and most of the property derivative would be done. So this requires the knowledge of EOS, equation of state. So we'll start with the equation of state to proceed further. So we'll start with now equation of state. So and the first equation of the state we have learned for the ideal gas. We have Boyle's law, Charles' law, one is saying V is inversely proportional to T, another is saying V is directly proportional to T, and from there we can get PV equals to 1. This expression you can write as V hat PT, or you can write this as P hat. So one of the functional form is available so far in our hand, which is valid for the ideal gas. Ideal gas is, my pressure is tending to 0, gas phase. The pressure is tending to 0, gas phase, but not for all the materials. If I have liquid, for water for example, I want to calculate dou S by dou P at fixed T. You cannot do it, because we have only equation of state available for the gas. As a chemical engineer, we cannot say, we are not like aerospace or gas dynamics people. Gas dynamics will only talk about gas. Even aerospace also talks about liquid and gas both. Metallurgists will talk about solid and liquid. Metallurgists will come to me and say, I want to have equation of state for solids. Chemical engineers say that okay, we talk about the gas, liquid, distillation column, all those things are actually mostly do liquid vapor. That's chemical engineering, right? We will say we want to have equation of state for liquid. Metallurgists will say no, that we have molten solid, we do casting and all. I want to have equation of state for the solid. So now our objective is to have the equation of state for the solid, liquid and vapor. Equation of state for the solid, liquid and vapor. So in order to do that, we need to see if we change the temperature with respect to volume, the TV diagram. If we have the TV diagram, what actually happens? If we have a T is a B axis and a T axis. Instead I have a solid. This is my point number 1. If I increase temperature, volume will expand. Solid, you know that V equals to V0 into 1 plus gamma T. Gamma is the expansion of thermal expansion. At this point, this is my solid. At this point, solid starts melting. When it starts melting, the volume will expand. Temperature is fixed. S plus L. So this is second point, third point. So third, this branch you can see temperature is constant, phase change occurring, volume is changing, but temperature is constant. At this point, remember that this slope is much steeper than this. This liquid expansion or volume expansion is not that fast compared to solid. Okay? This is liquid point. It is going up to that, again phase change occurs. It is liquid plus vapor. And then vapor. So started from here, we went to vapor phase, you can see the path. The path is not, this path cannot be a smooth function. It's a discontinuous function. Mathematically, this path travel from the solid phase to the vapor phase is not a continuous function. In T and B plane, it's a discontinuous function. Not a single function can represent this kind of zigzag form. And this is basically from physics. Okay? Correct? So then what actually happens? This occurs for a particular pressure. If I change the pressure, for this, pressure is constant, say P1. If I change the pressure, then you will get so there is a trajectory where this point will move, and there is some point beyond which, so this is, so what actually happens, this, and then this, okay? So, and beyond this point, there is no phase change. So that means there is a point which is called critical point. It happens in the liquid and vapor. So if I want to draw in a proper form the TV plane, what actually happens? This is my liquid point. I am a chemical engineer. I want to talk only up to liquid point. The last drop of liquid. So you need to have liquid and vapor. The last drop of liquid is here. Okay? So what actually I am interested on, so this dotted line will give the map, will give the domain where the vapor liquid mixture is possible. Vapor liquid. Here liquid, here vapor. Beyond a point, this is the critical point. Beyond a point, at this point what actually happens? We cannot distinguish between the vapor and liquid. Okay? And beyond a point, everything is gas. At this point, pressure is very high, here pressure is almost tending to zero. Gaseous. So beyond this critical point, you cannot distinguish between liquid and vapor. So most of the cases, we are below the critical point. And since we are below the critical point, we must distinguish liquid and vapor, and then we need to have equation of state to predict its behavior. So what the equation of state we have? This will give, if you want to do PV, this will give this kind of behavior. This does not give any indication of the phase change. It will give indication of the gas phase. Right? It will give indication of the gas phase. If I want to have vapor, liquid, liquid, vapor, phase change, I need to have an equation of state which can represent all the states. So I need to, so that gives the necessity to have the equation of state to predict the system behavior containing liquid and vapor at least. Solid for the largest, not for us. So if I want to draw the PV diagram, what actually happens to the PV diagram? The PV diagram will look like this is for different temperature where T1 is constant, this is T2 constant, this is T3 constant, and here some point, and here everything is ideal gas. So this is my complete PV diagram. This part is okay. This guy can do that, this region. I can have the ideal gas equation, my job is done. If I want to operate, this is my critical point. You have seen this diagram earlier. This each curve is called as isotherms because along each curve temperature is constant. Along each curve temperature is constant. It's called isotherm. Now my situation is typical case when I am below critical point. This is my PV diagram. I need an equation of state to have this kind of behavior. I need an equation of state this kind of behavior. That means I need to predict this is liquid, this is vapor, and this is liquid plus vapor. You can see that here at this zone, dou P by dou V at constant temperature and dou P by dou V at constant temperature. Here this is much deeper than this. That means it's not that much change. Here the change is quite high. The change is very small. The change is quite high. This flat means dou P by dou V at P constant, almost like so. This we need to have the evaluation. How to obtain it?
Why the change?
Huh?
Why the change?
Not the change. For the gas phase, what is actually happening? Liquid. Take the glass of water. Change the pressure. The volume will change. Do the experiment. If the gas, fully gas phase in the glass, if you change the pressure, volume will change very fast. That's why dou P by dou V is much higher than the liquid phase. These diagrams are all there in physical chemistry book. But we have not looked at the mathematical perspective. We are looking at the mathematical perspective. Now my question is, when the equation of state is, if I have a single equation, first of all, can a single equation of state will predict this? Answer is no, yes. Because this has discontinuity in the function. The function could have been like this, then okay. Now question is, we'll develop equation of state. We'll develop equation of state which will give this kind of function. This is hyperbola. Now I am developing equation of state. Now here in the class, I will tell you how to develop equation of state. How these van der Waals, all these guys going for developing equation of state is still this topic of research. If you want to do research on equation of state development, that's the objective, that's the way you should approach it. So for the ideal gas, you can see it's like a rectangular hyperbola. That's okay. We have done it. PV goes to constant at particular temperature. For this, we are going for this kind of things. If we have this diagram, there is a parabola, and you can see only one change of curvature. Here we can see there are two change of curvature. That means a quadratic curve cannot be sufficient for equation of state. A quadratic curve cannot be sufficient. This is a quadratic curve, right? Y square equal to 4x or x equals to 4 square y, whatever. A quadratic curve cannot be sufficient. So you need to go for the cubic curve. But we will see that how this behavior is. Will you give this one or something else, the cubic behavior? That's what the next fundamental equation of state is called as cubic equation of state. The next fundamental equation of state is known as cubic equation of state, and that's the first fundamental equation of state, which is van der Waals equation of state. First fundamental equation of state is van der Waals equation of state. VDEOS, van der Waals. First I show you the form and you see that it is exactly cubic form. Otherwise you cannot, so that's what one cannot have quadratic equation of state. Because we need to have two curvature change, and with that we cannot predict the entire behavior of the liquid to gas for the temperature range. So one cannot have quadratic equation of state. Now the VDUS. What is VDUS? Earlier, for the ideal gas, we have PV equals to RT. This pressure and volume, they play very important role. When you have a container, you have the gas molecules. When the pressure is low, they will be very compact. Sorry, pressure is high, they are very compact. Pressure is high, infinity. The pressure is low. One molecule here, one molecule here, one molecule here, one molecule here, one molecule here. That means maybe 5-10 molecules in a big jar. They will be just here and there. We can neglect the volume of the molecules, but if the pressure is very high, this volume of the molecules are very important. So available space for these molecules to move is less here than this, and effective volume for the moving will be V minus V. So effective volume for movement is V minus V. The first correction of volume. The high pressure. Low pressure means no problem. Effective volume is so much, we can neglect this V. The high pressure, only this much area is available for movement. So you have to subtract this guy's volume, say maybe 1000 molecules are there, 1000 into the meter cube, whatever is there, minus this will be the effective volume for the movement. Similarly, when these guys are quite a lot, they will be having attractive interaction and repulsive interaction with the molecules. What are these? When the two molecules are coming inside, the electrons will start repelling to each other, and the proton and electron and this proton and electron will be attracting to each other. So we will get this is called Lennard-Jones potential. This is called Lennard-Jones potential. What it says that during this regime, there is some regime which is repulsion because of the electron, and the beyond a point the attractive phase is quite less. So with that, so there is some kind of pressure change P star minus P, which is denoted as A prime N0 by V, N0 by V. It says that the observed pressure is less than the pressure in absence of attractive forces. So the observed pressure, the actual effective pressure. So the reduction of pressure is actually occurring, and the reduction of pressure. So because what do you mean by pressure of the gas? How it is heating this container? That's the pressure, right? If there are so many molecules, because of the attraction, the heating will be less. So actual pressure will be reduced. P prime minus P, which is saying that it depends on number of molecules per unit volume in that particular layer and the next layer. So that's why you have A prime N0 by V, N0 by V. So it is A prime N0 square by V square. So that's why we have P prime equals to P plus A by V square. A is actually having all this constant, A prime N0 square. So that's why my van der Waals equation of state is modified P plus A by V square, V minus V RT. And if you look at this equation in the PV plane, it's a cubic equation. So physics is also saying that yes, mathematics is correct. I need to have the cubic equation, because we do that it is PV square plus A V minus V equals to RT, and that's the cubic equation. So that's the philosophical perspective of the first equation of state. Yeah, so I'm done here. So next class will continue further.